Example 5.3. A circuit displays a battery and 3 uncharged capacitors. The switch is thrown to the left side until capacitor C1 is fully charged. Then the switch is thrown to the right. What is the final charge and voltage for each capacitor? So what we're seeing here is that there's two circuits. There are two circuits. I'm going to say that at t equal to 0, we have a circuit that only contains C1. So I have a voltage source here, and I have one capacitor like this. So this guy here is C1 equals to 4 microfarads. And then this is a 12-volt source here. Now the capacitor is going to get fully charged. So we know here is that this capacitor will then get fully charged. So that means here, when it reaches steady state, the voltage of the capacitor initially is then going to be 12 volts. Now, what's going to happen? Then at some time t, how about say at some time t greater than 0, whatever that time is, I now have a circuit that now reads like this. I have a fully charged capacitor, and this capacitor is now going to be in series with two other capacitors. Let me draw this just a tiny bit better. It's going to look like this. So this is going to be C1, and C1 is going to be fully charged, right? It's going to have full charge. Now I have two other capacitors, which are C2, which is 6 microfarads, and C3, which is 3 microfarads, and these guys are completely uncharged. So then we want to find out is what are the final charges. So in this state here, the question then reads like this. What are the charges of C1, C2, C3, and voltages V1, V2, V3? So it's the second circuit that we're most interested in. So the question is, what do we want to do right now? And just to remind you here is that this guy and this one, these are uncharged. Whereas C1 is charged. So what do I expect? What I expect is something like this. We're going to start off at t equal to 0. So at t equal to 0, capacitor C1 is fully charged at V1 initial of 12 volts with a charge of this guy. So then according to the capacitor equation, Q1 initial should be C1 times V1 initial. So the initial charge of the capacitor then is going to be 4 microfarads times 12 volts. So that should be 48 microcoulombs. And this is the initial charge of this guy. So now I know its voltage and I know its charge. So what do I expect? At some time t later, so when the switch is thrown, there is an unequilibrium situation, which implies here that now current flows. So when I'm looking at this circuit right here, and this is my circuit right here. So if I'm looking at this circuit right here, what I have is that I'm going to have some initial voltage right here, and that voltage is 12 volts. The voltage of V2 initially is 0. The voltage of V3 initially is also 0. So the fact that we have an unbalanced situation here, this really tells us that then V1 initial has to be greater than V2 and V3 initial, which means now that we have a voltage and current slash charge moves from C1 onto both C2 and C3. So what we're going to find here is that some of the charge is now going to go onto C2 and C3. So that means here that the initial charge of capacitor C1 is going to retain some of the charge, and then some of the charge is going to go on to C2 and C3. So let's start analyzing the circuit here. So we now know everything about what happened initially to the capacitor. Now we need to C1, that is. So now the switch is thrown. So now we want to analyze this scenario here. So let's do that. So let's analyze this circuit in detail. The first thing that I would do is that note that C1 and C3 are in series. And what we know about series is that they have the same amount of charge. So I would reduce C2 and C3, which are in series, into an equivalent C23. So if I do that, then I could see here that now 1 over C23 is going to be 1 over C2, 1 over C3, but using the trick, I could then write this as this combinations of C2 and C3. When I do that, then I'm going to get 6 times 3, 6 plus 3, which then gives me 2 microfarads. What does that circuit look like now? So the circuit now reads as follows. I have this circuit right here, and I'm going to modify this thing. I know that these guys are uncharged, but right now I don't care about the voltage. All I care about is these capacitor values here, capacitance values. So what I'm going to see is that I now have a circuit that then reads like this. So after a rewrite, I now have a circuit that reads where in this situation, this is C23, and this is 2 microfarads, and I'm going to run out of space, so let me move this over. And then I have C1, which is 4 microfarads. And so when I'm looking at these capacitors, what I'm seeing here is that this guy has some initial charge. And we've calculated this charge. We know that initially the amount of charge on this plate here is Q1 initial, and I think, what did we calculate? 48, I believe. Yeah, 48 microcoulombs. So this is 48 microcoulombs. So now what happens? So this is the circuit that I'm focusing on. So this side now forms a high. This end forms a low. So what we expect is charge to now move on to these plates. Okay, so in other words, I expect charge to now start moving downwards like this. And as a consequence, I'm going to build up certain amount of charge on these plates. So what does that tell me then? Charges will move from high to low potential. And redistribute charge Q1 initial, which is 48 microcoulombs, do the charges here. So when I look at this thing, here's what I'm seeing. I initially start off with Q1, right? So this guy right here, this is the initial charge. As a consequence, we're going to see is that afterwards, this is going to be the leftover charge. So some of it, so I'm going to have, there's going to be some leftover charge. And then the rest of the charge is going to go on to the 2,3 capacitor. So in this situation, we're going to say that this guy right here, this is the transferred charge from capacitor 1 to capacitor 2. So now, what do I know? The capacitors are going to reach steady state. At steady state, all capacitors have the same voltage. And so that means that the voltage of capacitor 1 has to be the same as capacitor 2, 3, where the initial voltage of 12 volts is then going to be greater than V1, which is equal to V23. So we expect that. So now, let's go look at this thing here. So I know about the charge. I know about the voltage. So now, let's put this all together. So when this occurs, we start with the initial charge, which we know what it is, and this is going to equal to charge on C1, and this is going to equal to the charge on C2, 3. And then the capacitor equation essentially tells us this, that this guy is going to be C1 times its voltage, and this one is going to be capacitance 2, 3 times its voltage. But we said that these guys are going to have the same voltage, right? We just mentioned that these guys must have the same voltage because there's only 2 nodes. Look at the nodes. Here's my high node. Here's my low node. There's only 2 nodes, so they have to have the same voltage. So then I could come in here and I can write a relationship that reads C1 plus C23 is then going to be this final voltage. So now I can calculate that final voltage. I know the total charge. I know the capacitance. One can now solve for the final voltage of these capacitors. So in this case, I can then see here is that that the voltage of 1, so if I look at this, so the final voltage is then going to equal to the total initial charge divided by the sum of the capacitors. So if I plug in my values here, capacitance 1 was 4 microfarads. This is 2 microfarads, and it all goes into our charge of 48 microcoulombs, which then gives us 8 volts. So in other words, this is also the voltage of each of these guys. Now, let's draw a picture to show you what do I see here. What I see is I start off with the circuit, and let's copy this. I think let's go back into here. And let's just copy this. So if I bring this guy into here, and what I really want to do here is that I want to sort of like look at the over all picture. So what I'm seeing here is that this guy is now fully charged. So we know here is that this guy right here has a charge of 48 microcoulombs. When the switch is thrown, but remember, we also know that this guy initially was 12 volts. So now what happens is that the switch is thrown. And as it's thrown, now I have something different that's going on. So what's going on here is that if I look at C2 and C3, we then reduce this down to one capacitor. This is capacitor 2, 3. And what we know about this capacitance is that this capacitance is equal to 2 microfarad, whereas this guy, C1, is equal to 4 microfarad. The charge redistributes. Now over here, we had a voltage of 12. Now over here, we have a different voltage. This voltage, so if this is the ground right here, so that means this is 0 volts here, this is 0 volts. We're seeing that this guy rises up to a voltage of 8 along here. So this node right here is 8 volts. So now I can actually go in and start to calculate the charges on each of the capacitors because I know the voltage. So then I could see here. So the remaining charge on C1 is then going to be, I could then see here is that I'm going to have this capacitor right here. And I know that this is C1, which is 4 microfarads. We know that right here, it has a drop of 8 volts. So this immediately tells us that then the charge that remains, according to the capacitance equation, is then going to be this final voltage here. So in this situation, it's going to be 4 microfarads times 8 volts. It's going to give me 32 microcoulombs for the remaining charge. Now I can repeat the same process for Q23. So repeating for C23, we could then say that now I have this guy, which is now C23, which is equal to 2 microfarads. And once again, this guy has an 8-volt drop. So if I now go and I calculate this current, not current charge, this will be C23 times its final voltage. And in this situation, we get 2 microfarads times 8 volts, and that's going to give me 16 microcoulombs. And that's going to be for charge 2, 3. So I now see that I have this amount of remaining charge on one of the capacitors, and this is the same for that equivalent capacitor. But remember, these guys are in series. So that immediately tells us that because they're in series, they must have the same current or charge. So therefore, the charge on 2 has to be 16 coulombs, And the charge on 3 must also be 16 microcoulombs. And that's because they're in series. So in summary, this is what we end up having. I started off with an initial capacitor. It had a voltage of 12 volts, and it had a capacitance of, I forgot what the capacitance, I think it's 4 microcoulombs, microfarads, excuse me. And we know that it had some initial charge. I believe it was 48 microcoulombs. Now we have a thrown switch. So when we throw the switch, I now have a circuit that looks like this. And so when I look at this circuit, what I'm going to see here is that this guy, C1, well, this guy now has a voltage drop of 8 volts. Okay, it has a voltage drop of 8 volts. And when I look at the charges here, I could see that the charge on this guy, this is then going to have a charge of Q1, which we just calculated, which is 32 microcoulombs. So when I look at C2 and C3, I also see that these guys have a charge. This guy will have a charge of 16 microcoulombs. This one is going to have a charge of also 16 microcoulombs. And once again, this is C2 and C3. So the thing that's missing here is that we don't have the voltages. So now the voltages of the capacitors, each of the capacitors then has to be this. So then the voltage of 2 is going to be the charge of 2 divided by the capacitance of 2. And in this situation, the capacitance of 2 is, I forgot what it is. It is, I think it's 6. So then I'm going to get 16 microcoulombs. Nope. Yep, microcoulombs. And then the capacitance is 6 microfarads. So that's going to give me 8/3 volt for delta V2. When I go to delta V3 here, that's going to be charge 3 over C3. And this will then give me 16 microcoulombs. And that one is 3 microfarads, which then gives me 16/3 volts for these voltages right here.